All right, we should be kicking in. There we go. I'm just pulling up the link so I can drop that in the channel. Hold on. Okay. All right, here we go. So the reality is, you know what I might do as long as I'm on a roll here? We've got technically the whole week to hit this, but what I think I'm going to do, so first of all, the way we're wrapping this thing up is we do this last lecture, which, like I said, scheduled for 2, but can easily go 1, depending upon how I do it. What I might do, since I've got both class periods right now, is actually just roll through and do the whole thing right now. Then lecture's done, you can hit it whenever you're ready. And then on Thursday and then the following week, which is the last week of semester, Thursday and then Tuesday, Thursday of next week, whatever that turns out to be, 6th and the 8th, we can just do kind of help section. Something I don't understand. Can you look at my code? I can, whatever, catch up on any grading or help you with, can you open the exam and, show me what I did wrong? Any of that kind of stuff. We can do either group setting or one-on-one during the class periods on this coming Thursday and then next Tuesday, Thursday. So I think I'm going to do that. I think I'm just going to plow through and be done with this. Then lectures are done. Um, that sounds good. And by the way, for the small handful of well-wishers, I'm doing fine. Just some upset stomach. I don't know if it's Thanksgiving or it's not COVID, but that little bit of upset tummy just made it uncomfortable to try to work my way to campus. Plus, I don't know. I think that we need to have an abundance of caution at all times, just given the pandemic and everything. Who knows what symptom is what anymore. So best to be on the safe side. And would encourage all of you, to the extent possible, to play it safe. The other thing too, just as a reminder, I was able to discover that Canvas has in fact been recording in-class lectures that have been going on. And sorry, I need replacement agua. Canvas has in fact been recording live classes. So even if you don't either have access to or want to have access to what I've posted on YouTube from my own in-class recordings, that notwithstanding, there are recordings on Canvas, and I have made those recordings. There's a thing I have to do on Canvas. Sorry, I made a mess with some water. There are things I have to do on Canvas to make those become visible, and I did those things. I did those very things on Canvas. So you should be able to see all the in-class lectures from Canvas. And I understood that a lot of those cameras weren't functional, and so I was able to make that work. And when I got in there and looked at it, the cameras were working, and I don't know about the rest of the quality, but I do know that they're there. Okay, so let's hit this thing. So this is, we're talking about queues and stacks. In particular, we're going to start with stacks. The stack is a data structure. It is a very well-known and important data structure, as is the queue. And I think you pick these up. There is a point where you pick these up in your courses. 1410. I don't know, 2420, is that the other one? But you do get to them before too long. Um, okay, so and by get to them, I mean like, build them, code them, use them a lot more extensively. But so this is probably for many of you your first actual introduction. Um, the stack data structure, they sometimes call it a LIFO, last in, first out. The idea here uh, is that, okay, a couple of things. The independence of the actual implementation means that you can build these things different ways, but as long as you've got this ability to take something is added to a stack, added, and then when you go to access it, you access it from that same top. So the last item on the stack is the first one you pull off. Okay, in contrast to a queue, which is a line, and the last one in the line is the last one out. First come, first served is a queue. Okay, sometimes called a FIFO, which we'll get to. But the LIFO is very much the stack, which will, show you some ideas here. In fact, let me just, these are examples of stacks. The stack of letters, stack of pancakes, stack of plates. The analogy breaks down in this instance though, because you can obviously, reach into the stack of mail and pull stuff out, and which is also true of some stacks actually. Or, that when you're doing plates and you put away a whole bunch of plates, you put three new plates on top of, clean plates on top of an existing stack. So the metaphor breaks down because in an actual stack, let me back up. In an actual stack, I push items onto the stack, I pop them off the stack. That's the term we use, push and pop. Okay? I detect overflow. This is homework bingo, by the way. I detect overflow because the data structure has a limited amount of space. Remember, everything in the computer has a limited amount of space. So the overflow simply means that the stack is full, the space is full. It's like when you try to put plates, in the cupboard and there's not enough room. You got one more plate you want to put and you can't get it in there. You can't slide it on the top. That's overflow. When you attempt to push and you can't because there's not enough room left. And underflow is when you try to pop, but the stack is empty. Okay. But so these guys break down because when we live with them in our real life, we don't strictly access the thing on top is the one that goes on and it's the one that comes out. However, in this instance, we do. This is my best, very, very best analogy for a stack data structure. Okay. The infamous shopping carts. And the reason I say they're infamous is because one of the things that happens is that all of, let me see if I can get my mouse over there. Where's my mouse? Hang on. There we go. What you can kind of see is that there's this concrete barrier along the side. I don't know if you can see my mouse moving. Concrete barrier along the right side goes down. At the back end, there's a concrete barrier and a concrete barrier down the left side. Okay, now what that does is if you want, this particular cart that has a sticker that says 1886, I don't know what that says. Yeah, 1886. And you want that one, you have to pull the one out, then you have to pull the other one out, then you can grab that one. You got to pop a couple of carts off the stack. So in this case, the bottom of the stack is at the far end, and the top of the stack is on the near end. And when I'm returning a cart, I return it to the top. By the way, I just want to double check something. Hang on a second. Okay. Sorry, I'm okay. That should be better on the audio. That's sorry. That should have been picking up from the built-in, but I hope that was picking up. Yeah, I know it does because I checked it when I first loaded the video. Anyway, but you get the idea. That's the stack structure. The last one. What I hate about this is that all of these carts up here on the close side, if it's a low traffic day, you're only going to go like 10 carts deep, right? Depending upon how many people are in the store. Then you put the same ones back, pull the same ones off, and the ones at the end aren't getting used, so they're not wearing evenly. So that's a thing. There are, in fact, grocery stores. Walmart tends to do this where there's like Costco tends to do this where there's an entry point and then an exit point. That's a queue. So the carts are coming in and then you pull from the front, you pull the nose of the cart out and then use it. In this case, you back the cart out because you're popping from a stack. Okay. So here's an example, and it's really it's a little bit tricky to build one, and I'm not going to make you build one. Now, if we had a longer semester or, more credits or something, then this would be a great thing to have you build in assembly language. But the bottom line is that I've got this stack that has the number 1 on it and I push a 2. Now this is what my stack looks like. I push a 3, now that's my stack. I push a 4. The numbering on this, I didn't make this graphic. I borrowed it, but I don't like it because the numbers are not random. It looks like you have to push a 2, then a 3, then a 4, then a 5, then a 6, and that's not true. It just is showing that I've got the stack that happens to have 1, 2, and 3 in it, and I push the value 4 and I get this stack. Push the value 5, I get that stack. See the idea? And when I'm pulling values off, I pop and the 6 comes off. I pop and the 5 comes on. Now notice the difference. When I'm pushing, I push the 2 and now it's on the stack. I push a 3, it's on the stack. I push a 6, it's on the stack. But when I pop, I don't pop a 6, I just pop and the 6 comes off. I pop and I don't know what's coming off. When I'm pushing, I'm taking the thing that I'm pushing and I hand it over and I push it on the stack. When I pop and when I have the result of the pop is a value. Okay? So this is a little bit super duper contrived. But I got some better examples maybe. Excuse the resolution on the graphics here. I know I should just rebuild some of my own. What this one doesn't really, this shows you graphically that I push it like I stack it on the top. What this one does, then it's a little bit more reasonable, is to reflect the idea that I make a call like a push the value 2. And what happens is 2 goes on the stack and there's a top pointer. And in this case, now keep in mind, remember when we talked about memory? Your memory could start at the bottom, memory starts at the bottom, but the bottom could be represented by the top of your page or your screen, or you know what I mean, where memory grows this way, like in the LC3 simulator, or memory could be flipped where the bottom was down here and you could represent it both ways and it didn't matter. Well, same thing here. You could represent a stack as being starting at the top and growing down. I push and it goes down. I pop, it goes back up. Or flip this way where I push and it goes up and I pop and it goes down. Similarly, I can put this top pointer pointing to the last item, or I could have it pointing above the last item. It doesn't matter really in practice as long as you're consistent about how you deal with pushing and popping. In this case, top, we push 2, 2 goes on, and top points at the top item. Okay? Then I push 5. Now again, what I don't like about this is that I've got a bunch of pushes. No, there is a pop, then a push in between some pops. I push a 5 and now top is there. So when I push a 7, what really happens is I move top and I put 7 there. Top is just a pointer. I push 1, so I move top and I put a 1 there. Now I pop, and the answer is to pull the 1 off and return it to whoever called that pop. Then I can push 21, and again, I move the top up, and I write 21. Now I can do a pop, and so I take what it points at, 21, I return it, and then I decrement top, and I just keep going. That's how I push and pop, okay? Now, this is another one about implementing this in memory, okay? And what I'm showing you here, so this is in more like an LC3 kind of environment, okay? And so we've got these are just memory addresses, 3FFB, C, D, E, F, right? These are snapshots. One view of the memory, another view of the memory, another view, and another view. We're using R6 as the stack pointer. Could be anything. We're just using that, okay, for the sake of our argument, our discussion. We start with, and notice that we are right. The top starts at 4000 hex 4000, which is known to our implementation to be below the stack. Okay, it's known to be below the stack, and so the next thing that happens is that's the initial state. After one push, I push the value 18. I move the top pointer up one, but our memory goes from the bottom down. So I'm decrementing R6, right? Now R6 points at this one, and I put the value 18, what they were pushing right there. Now I do 3 more pushes, and each time I'm going to decrement R6 and put the value, decrement R6, put the value, decrement R6, put the value. Notice that now R6 is 3FFC, okay? Now, then I pop twice. I pop and the 12 is returned and R6 gets incremented 1. I pop and the 5 gets returned and R6 gets incremented 1, so it's now 3FFE. Now, why is 12 and 5 still there? Okay, remember when you copy a value, move a value, the value is still there in memory. So the trash left over on the stack, and there's some famous security breaches that are based upon this fact that you push up on the stack, and then when you pull away, there's still stuff there. If you just move past where the stack pointer is. But that's sort of a more of a kind of a core implementation. And if we had an assembly language, which we don't in the LC3, but we do in almost every other assembly language, actually like a push, we could do this thing by saying, have a stack known value and say push some value, right? And in this case, we'll say that the value we're pushing, we put into R0, okay? But if we didn't have that built in, we could write our own. So we define push, that's a label. Add R6 to -1, decrement R6, put it back in R6. So to add, I decrement R6, and then I take the value in R0, which is the value that we're going to push onto the stack, and we push that value to a store R, where R6 is our pointer, and we put that value into memory. And when we do the pop, it's really just the inverse. We load R from R6, whatever R6, like right here when we do the pop and R6 was 3FFC, I'm going to load from whatever R6 is pointing to, which is 3FFC, and I'm going to put that value in R0. So 12 would go into R0, and then I would have the value. And then I would add 1 to R6, which moves that pointer down. So that's one way to write that and to build, push and pop operations in assembly language if you don't have it already. Okay. Now, one of the things we do with math, with stacks is certain kinds of math. Okay. Now let's take something like A plus B, the quantity times C plus D. And this is what we already know. Now I'm assuming there's a multiplication function, which we don't have in LC3. Fine. But these are just dot fill values, and E is a block W of a length 1. So that's where I'm going to put my result, the store R0 into E. But if you look at this, I hope you can see my mouse bopping around. Um, this is what you already know how to do. You load R0 from A, that has a 25 load, R1 from B, so R0 and R1 are A and B respectively. I add them together and I'll just store my result into R0. So this quantity A plus B is my value R0. Then I load R2 and R3 with C and D. I add them together and put the result into R2. So now I've got R0 is this quantity on the left and R2 is this quantity on the right. Then I do a multiplication that, again, I don't have a mul operator, but I do it because I'm assuming I do, of R0 times R2. I put the result into R0 and I store the result into E. You already know how to do this, but how would you do this um, if you had a stack-based language with pushes, pops, and still have adds and multiplies, okay? Here's what you would do, and we're going to kind of roll through um, the operation on this one, okay? I push 25, then I push 17. Now, when you do an add operator in a stack-based language, what happens is the add operator is a binary operator, meaning it has two operands. So I pop the first one, I pop the second one, I perform the operation, I get the answer, and I push the answer back on the stack. That's how it works. Not hard. So when I do the add, notice I got 17 and 25. When I do the add, I pull them both off, add them, and push 42 back on. Then I push 3, I push 2, and I add them together. So it's going to pull the 2, pull the 3, add them, make 5, and put the 5 back on. Now to do a multiply, what's going to happen is it's going to pop the 5, pop the 42, multiply them together. What is that, 210? Multiply them together and push the result back on. There it is. And then finally, I'm going to pop to put it into E. And then the stack pointer goes back down to zilch. Okay? That's it. That's the stack. That's all you have to know in this class about the stack. Well, not quite. I mean, almost. The stack is very commonly used in operating systems. You know how sometimes we'll be in, you'll go into you're about to make a function call, but you don't want to screw up your register. So in LC3, where there's no stack operators, I have to do things like take the registers, save them away, and then when I'm done, I can, bring them back. Well, when you have a system stack, what you can actually do is take register A, register 1, whatever, and just push it. Oh, excuse me. Just push A, push B, push C, push D, make your call, and then pop D, pop C, pop B, pop A. So you can you can really quickly store stuff away and then get it back. But you just have to push it and then pop it in reverse order. Okay? That's it for the stack. I'm looking, nobody's on the chat on Discord, and that's fine. And so I'm going to drop off that chat just to not hog it. Let's talk about the queue. This is our second half of this discussion. Queue, it's what the Brits call a line. We say get in line, and the Brits say get in the queue or queue up. Okay? So, like a lot of people, first come, first served, last come, last served. Okay? You insert items into the back of the queue and you remove items from the front. We sometimes call it a FIFO. There's a lot of stuff like keyboard input that arrives in order. It arrives sequentially. And the order that you type, right? You don't want to just have a bunch of random characters just showing up, at different, out of order. It would make no sense. I type a letter, you need to save that, but I got to put it into a queue. Put the next one, put the next one. Then when you pull values out of the queue, you're pulling them out in the order that they arrived. Okay? Oh, you guys are so boring. That's why it's so tiring. Okay. That's it. So here are some examples. I'm going to show you, in fact, what have I got here? This is it. There's some animation on this, and this is the end of the lecture. So really, I said this wouldn't take a whole class period, um, barring the amazing questions that commonly get asked by the, well, by both sections, but um, I normally record the first section. So, all right, so here's a queue as a data structure. These are locations in memory, 8000, 801, 02, 03, 45. This is R3 and R4, which are holding on to the values of front and rear. Okay, remember I add things onto the rear and I pull them out of the front. So I'm using R3 as my front pointer and R4 as my back pointer. Notice that with a stack, I needed to have something to show me where the bottom was, or it just has to be coded and understood to be where the bottom is. But mostly I had this stack pointer moving up and down. What I'm showing here is when you're using a queue with the stack, I can say I've got this much space, and I go up, and when I hit the top, I'm out of space. Okay, and that's fine. But with a queue, I guess for some reason I feel like when I'm doing a queue, I want to spread it out more linearly, kind of horizontally. But if I've got a limited amount of memory, I move my front and back pointers, and then I can actually wrap around, and they'll follow me around, and they'll kind of chase each other around, uh, through the queue. So in this case, I've got a queue of only 6 characters. Okay, R3 is the front, R4 is the back. So what I'm going to do, let me see, what is this guy doing? Oh, yeah. I'm going to consume the value at the front, which is 17. So when I consume, so I do a remove, okay? And that gives me this. It pulls the 17, hands it to whoever called the remove on the queue, and then 17 is still there because it's just garbage left in memory. But the front moved. Notice it moved from there to there. That's my front now. There are 3 items. Right now there were 4 items in the queue. I removed the 17. Now there's only 3 items in the queue. And notice that R3 changed value. Now I'm going to insert the value 10. Where do I insert? At the back. Okay, I remove from the front, insert at the back. So what I need to do is put the value, notice I'm going to insert 10. So that 10 has to go, I've got to extend the rear here one more and then put the 10 there, which is what I do, and that gets me to here. Now, what ought to be obvious is that I'm right on the boundary now. Here I was in the middle with room to spare. Now I'm right on the boundary. So what I'm going to do is insert 20. Okay, now the problem is I can't simply, the logic is more complex than the stack. With the stack, I just go until it hits the bottom. With the queue, I don't know what my problem is. Really, it's the lack of questions and the lack of standing up, walking around. What I have to do is when I decrement the rear, I actually have to wrap it around. And that's what you see over here. Rear gets wrapped around to here, and then that's where I put the 20. Notice again, I'm inserting 20. Rear can't go down, it's got to go back up to here where there's space. I'm not in conflict until I collide. Okay? Now I'm going to insert a 30 and insert a 40, okay? When I insert the 30, oh, you know what? I think the front, I'm looking back at this now, based upon what this does, that the front is not pointing at the element I'm popping off or removing, it's pointing out one. So when I did the remove here, let me see. Yeah, notice it didn't say what the value was. When I'm removing here, I'm removing the 23. So I move the front back and then return that value. That's what I'm actually doing. And everything's been insert. When I insert 30, I put the 30 where the front points. No, which I put the 30, sorry, front is pointing here. This is not right. I don't think this is right. Oh, no, 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 no. I inserted the rear. So I increment rear and I put the 30. I increment rear again and I put the 40. Now, this is where the logic gets a little bit tricky. The rear and the front are pointing to the same spot. The rear is pointing at the last item that was entered, and the front is pointing ahead of the one you would actually pull out if you do a remove. And in fact, yeah, this one doesn't actually do anything more. Again, this was just borrowed from the McGraw-Hill stuff. I hope that makes sense. You don't need to implement this. You don't need to do it. It's a good exercise to do it because it really makes you think like really clearly about what's going on with stacks and queues. Just in my view, just a little bit premature. But what I do want you to understand is that when you're doing a stack, you're growing bump, bump, bump up, and then you're going bump, bump, bump back down. And with a queue, you're always tracking the front and the back so that you're always removing from the front and then inserting on the back. So as you're putting stuff in and taking stuff out, you're sort of you're cycling through that limited finite amount of memory. Okay, now that is in fact that's the end. That's the end of stacks and queues. Um, and I have no problem just starting. Obviously, there's nobody live right now, and I'm fine with letting this just kind of post. So I'm going to go ahead and stop, and then I'm going to be available. If there are questions on Discord, please hit me up. You can DM me, or you can hit me up in the DM queue, or hit me up on the general channel, and I'll just be there. That was only 37 minutes to get through all that. Again, Thursday is going to be a help section day. If you're killing it and you don't need to come, don't worry about it. If you want to come and either share in whatever people are doing and are having questions about, then knock yourself out. Okay, I will catch you all on Thursday. I'm really feeling fine, just a little under, and best to not take the chance today. So I'll be fine to be there on Thursday.